Well, my dear participants, I have made certain changes in the file. So, I would like to run the document so that the PDF can be generated. So, I will go into knit button and then knit to PDF I will run. Yes, now I will go into file and open the PDF. So, these things we have already discussed. I am still continuing in sampling distribution using R. I have already talked about chi-square distribution with 5 degrees of freedom. Now, with 30 degrees of freedom, chi-square distribution with 30 degrees of freedom, we expect it to be approximately normal. So, we will issue the command chi-sq30 replicate is equal to replicate, first argument is 1000 simulation, expression sum r norm 30 square. So, it will generate 30 random samples from the normal distribution, standard normal, 30 random sample, and then it will compute its sum, and then we are making histogram of the sum, which is nothing but it follows chi-square with degree of freedom 30. So, this is the chi-square. Now, some problem with these things we have already discussed. I think I have already discussed these things. Yes. Now, another problem I have already discussed these things. Yes, students t distribution. Students t distribution with here I have already discussed these things, t with 5. Now, f distribution. F distribution, if x follows chi-square with nu1 degree of freedom, y follows chi-square with nu2 degrees of freedom, and both are independent, then the ratio of the two chi-squares variates divided by their corresponding degrees of freedom is termed as F distribution. Mathematically, F ratio is nothing but x divided by the degree of freedom. X follows chi-square random variable, and it is being divided by its degrees of freedom, and that is nu1, and whole divided by y, which is again a chi-square distribution with nu2 degrees of freedom. So, we are dividing it by the chi-square with nu2 degree of freedom, the corresponding degree of freedom. So, this ratio follows F distribution. Now, how we can implement this? F is equal to replicate 1000 times, and we are writing the expression R chi sq df is equal to 5. So, it will generate here in this expression, it will generate one random observation from chi-square with degree of freedom 15 divided by the 15, and histogram F distribution y limb, and then curve df F distribution, density of F distribution, df1 is equal to 15, and df2 is also 15. So, this way we are having R chi sq yes. There is some mistake in this expression. So, I will correct. First, I will correct this. There is some mistake inside the expression. F is equal to replicate, n is equal to 1000, expression is equal to R chi sq. This is this. and here we can write one more bracket, and then we are going to use this bracket. Now it is correct expression. Yes. So now the expression has been corrected, and this is the simulated data, and we are getting the result. So here we have expression for simulating. Here you just try to understand this expression. What we have done, we are trying to simulate this ratio. So in the expression we have written arc-ISQ, 1 observation with degree of freedom 5 and divided by 5. Then in the denominator also arc-ISQ, 1 observation and degree of freedom is equal to 15 divided by 15. And this expression is to be computed how many times? 1000 times. So that way it will generate 1000 random deviates, and then we are making the histogram and we are getting a curve. So now after making these corrections, I will generate the PDF. So before generating the PDF, we will just close this file which is open. If PDF is open, it will not generate. Now we will go into net, and here we will make the corrections, and after that we are generating the PDF from the source file. Yes. Now PDF has been generated, and we can open in the PDF. We can open the PDF and see. This is the F distribution. These are the commands. Now these are the corrected commands, and this histogram is made on the simulated data, and this one is the exact F distribution, the curve of F distribution with 5 and 15 degrees of freedom. So this way we are matching both the things. Now a relation between T and F distribution. It is a well known fact that if Z follows normal 0, 1, and then Z square follows chi-square distribution with 1 degree of freedom. What happens about the distribution of T square when T follows T distribution with new degrees of freedom? It follows F with degree of freedom 1 in the numerator and degree of freedom nu in the denominator. This fact could be provided by the simulation. Actually, if we go into the expression of T distribution, just I will go and I will explain. This is the ratio of 2 chi-square divided by their degree of freedom. So this is F statistic. And if you go to understand T distribution is what? T distribution is nothing but it is the ratio of two variables. The numerator is Z normal 0, 1, and here X follows chi-square with 1 degree of freedom. If we make square of T, what happens? It becomes Z square. So Z square is nothing but it is chi-square with 1 degree of freedom divided by the 1, and this also becomes, after squaring, this square root removes and X divided by the degree of freedom. So it becomes T square becomes F distribution with 1 and K degrees of freedom. So same result I have tried to express here in this expression. So T square. Now T is equal to RT, 1000, degree of freedom 20, F is equal to T square, the random observations, 1000 random observations from T distribution with degree of freedom 20, and F is equal to T square. Then we have made histogram of F, prob is equal to true, and then we are adding a curve DF F distribution X, DF1, numerator degree of freedom is 1, denominator degree of freedom 20, add is equal to true. So this will give this curve. This is the F distribution with 1 and 20 degrees of freedom. So, this is the curve. So, now we can go into the source window and we can run a relation between T and F. We can run these commands by just clicking here. So, this is the F distribution with 1 because it is T square with 1 and df2 is equal to 20 degree of freedom. So, both are matching. So, that means our result is correct. Now, I am going to talk about a relation between gamma and beta distributions. So, here I would like to look into the PDF, a relation between gamma and beta distributions. If it is a well known result in statistical theory, if x1 follows gamma with k1 by 2 and with shape parameter k1 by 2 and rate parameter 1 by 2, it is what? It is nothing but a chi-square distribution with k1 degrees of freedom. And x2 follows also gamma with k2 by 2 and rate is equal to half. So, it is nothing but chi-square distribution with k2 degrees of freedom. Then u is equal to x1 by x1 plus x2 follows beta distribution with shape 1 is equal to k1 by 2 and shape 2 is equal to k2 by 2. This fact could be proved here by making simulations from gamma distribution. So, these are the simulations. x1 is gamma, R gamma means 1000 random observations from gamma distribution and with k1 degree of freedom, k1 is 10, so 10 by 2, k1 is 10 by 2 and rate is half. So, this is nothing but R gamma distribution with k1 by 2 and half. So, it is x1. Then x2 is another gamma random variable which is having 1000 simulations from gamma distribution and with k2 is equal to 12 by 2 and rate is equal to half. So, these two simulations are being made. Then we are going to talk about this expression u is equal to x1 divided by x1 plus x2. Actually, analytically, it is difficult to derive. It is although Rao CR has given his this derivation in his great book on statistical inference and introduction to linear statistical inference and its applications, written by C.R. Rao and published by John Wiley. Its first edition was published in 1965 and second edition was published in 1973. So, that is a great book to read, that is known as Bible of Statistics. That is C.R. Rao's contribution. C.R. Rao was a great statistician and he was the only PhD student guided by the father of statistics, that is Sir Ronald Fisher. Father of statistics, Sir Ronald Fisher, guided only one PhD in statistics and that too was an Indian and he was C.R. Rao. So, I have taken this result from C.R. Rao's book. So, now we are going to verify. Instead of using Jacobian analytic tool, we are going to use simulation tool. And here this simulation tool supports this analytical fact because we are adding, after making a histogram, we are adding a beta distribution with 10 by 2 and 12 by 2 on the histogram. So, this is the result. This is the result. This is the result. So, if we go into, this is the histogram, a relation between gamma and beta distribution. So, see, these two results actually match. So, I am going to the source code and I would like to run this result. See what we are doing. We are running x1, 1000 gamma random variables, control 2, x1. These are 1000 random gamma variates with degree of freedom, with shape parameter 10 by 2 and rate parameter half. And then x2, another gamma random variable which is having shape is equal to 12 by 2 and rate is equal to 1 by half. And then we are going to define this expression x1 divided by x1 plus x2. And this u random variable should follow a beta distribution with 10 by 2. So what we are doing, we are making a histogram on the simulated data u, and then we are adding exact beta distribution with shape parameter shape 1 is equal to 10 by 2 and shape 2 is equal to 12 by 2. So if we run, we can get the histogram. See, histogram is made on simulated data, whereas this one is the exact curve of beta distribution with shape 1 is equal to 10 by 2 and shape 2 is equal to 12 by 2. So both are matching, so that means our result is correct. Now I am going to talk about sampling distribution. Here I would like to read into the PDF. Sampling distribution of sample variance S square. It can be proved that if x follows normal mu and variance sigma square, then the sampling distribution of n minus 1 into sigma s square divided by sigma square, where s square is the sample variance, follows chi square with n minus 1 degree of freedom. This is a very standard result, and this result is available in all standard text, including C.R. Rao's book on linear statistical inference and its applications, or we can see these results in the book of George Casella and Berger, Statistical Inference. It is also a great book. So both the books have this result, and it is a very fundamental result in sampling theory. So here we can prove this result. So what we are doing? We are simulating 1000 observations from this statistic. So what we are doing? 10 minus 1 into, we are trying to write this expression 10 minus 1 into where this is the sample variance of 10 observations with mean is equal to 5 and SD is equal to 2, and divided by sigma square, and that is 2 square. And then we are generating a histogram, prob is equal to true, and then we are adding a chi-square distribution with degree of freedom 10 minus 1 on this histogram made, and this is the result we are getting. This is the result. See, this is the chi-square distribution, simulation from chi-square distribution with the number of observation is 10. So it will be 10 minus 1. It will be 10 minus 1 degree, that is 9 degrees of freedom. So this is simulation from chi-square distribution with 9 degrees of freedom, and this histogram is made on simulated data, whereas this density, the curve, is exact curve of chi-square distribution with 10 degrees of freedom. So this all proves about sampling distribution of sample variance which follows chi-square. So we have proved this result by through simulation. Now another result, that is sampling distribution of sample mean. It can be proved that if x follows normal with mean mu and variance sigma square, then sampling distribution of x bar follows normal with mean mu and variance sigma square by n. This fact could be proved instead of going for analytic derivation. We are proving this result through simulation. So x bar is equal to replicate, and here expression mean we are simulating here R norm stands for 10 random observations with mean is equal to 5 and SD is equal to 2. So, and then we are computing its mean, and this process is being repeated how many times? 1000 times. So, that way we are trying to simulate 1000 random sample means, and then we are making a histogram and we are adding a curve. Mean is equal to 5 and SD is equal to 2 by 2. This is 2 by, actually SD is nothing but square root of this expression. So, SD is equal to, because in R it talks about SD, not about variance. So, it will be SD square root of square root, this is the square root of 4 divided by, so that will be 2 divided by square root of 10. So, this is the SD, this is the SD, and this is nothing but standard error of mean. So, we are getting this result and we are getting the graph here, histogram of X bar. See, both simulation and histogram, they are matching. So, that means our simulation is correct. So, we have proved this great result also. It can be proved that X follows normal with mean mu and variance sigma square. Then sampling distribution of X bar is normal with mean mu and variance sigma square by n. So, we have proved both the results. The number one about sampling distribution of variance. So, that is n minus 1 S square by sigma square follows chi square with n minus 1 degrees of freedom, and X bar follows normal with mean mu and variance sigma square. So, these results we have not proved analytically, rather we have proved with simulation. So, these are the two great results in statistics. And if we look into, if we go into here sampling distribution, we can run these results. See, this is the result of sampling distribution of variance, which is nothing but chi square with 9 degrees of freedom. So, histogram, and this is the curve. This is the curve DF 10 minus 1. And about sampling distribution of mean, we have already run these results. X bar, see, X bar control 2, X bar. So, what are these observations? These observations are nothing but they are sample means, 1000 sample means from means generated by, this is the R norm. I am trying to express this fact. This is the R norm, 10, mean is equal to 5 and SD is equal to 2. So, we are simulating these 10 random samples, 10 random observations from normal distribution with mean 5 and SD 2. And then what we are doing? We are computing its mean. So, mean of this expression. So, this is 4.848, and see how many times these are. Say for example, if we will run this again, it will have a different mean. If we will run it, it will have a different mean. If we will run it, it will have a different mean. So, how many times we want to generate? 1000 times. So, 1000 sample means we can get. So, that replicate function facilitates this computation, and we are getting 1000 sample means, and that is nothing but X bar. So, that is nothing but X bar. And then we are making a histogram. X bar, prob is equal to true, Y lim is equal to C 0.7, and then we are adding a curve D norm X, mean is equal to 5, SD is equal to 2 by square root of 10, add is equal to true. So, if we run this X result, we are getting, this is the result. Now, see what is the effect of, just I would like to read it from here. We have already proved these two results. Now, meaning of large sample in CLT. When parent population is symmetric, then very small sample could serve as a large sample. For example, think of a case when parent is student T with 4 degrees of freedom and sample of size 5. So, what we are doing? We are replicating, we are getting means from T distribution with 4 degrees of freedom. So, 5, and we are generating its histogram and then we are computing its. So, these are the simulated data. So, simulated data and the exact curve both are matching. So, that means our simulated data is very close to the exact curve, and actually this is what we wanted to see. When n is equal to just 5, what will be effect of sampling distribution. Sampling distribution is very close to the exact distribution, which is excellent. Another example, when parent is logistic. So, here if we will use logistic distribution as parent population and we are generating a sample of size 5, see again n is equal to 5 is excellent to n is equal to infinity. So, when what happens when parent is skewed? So, when skewed, say for example, when parent is exponential, standard exponential. So, this 5 sample size does not work well here, because this is the which is not excellent. For n is equal to 20, what happens? For n is equal to 20, it somewhat improves, but still it is away from the central limit theorem, because it is not close to the normal distribution. It is not close to the normal distribution. So, this is all about which I wanted to talk in sampling distribution. My next talk will be about the linear models.